We are in S domain and we examine this frame. This frame tells us when we transfer to circuit theory S domain what happens. What I mean by saying that, what would be the changes, Kirchhoff current law and voltage law equations in S domain, and what would be the definition relation is in S domain. Definition relation of the elements in time domain, what would that be in S domain? We have examined it, that's we've finished. Now this video is about this frame. This frame tells us serial parallel connections, how we are going to use serial parallel connections in S domain analysis, and what is the benefit and application of it. We're going to see it. Let's go in. What it says here, S domain advantages over time domain. In time domain, serial parallel connected resistors only, or only capacitors, or only inductors can be replaced by an equivalent resistor, capacitor or inductor correspondingly. This is not true for the mixture of these elements. What we are saying here, if there is a resistor and a capacitor connected in serial, you cannot replace those two with one equivalent element in time domain. But you could replace those two with an equivalent impedance in frequency domain and S domain. So that is a comparison of three domains. In time domain you cannot do that, but in frequency and S domain you cannot find the equivalent element impedance, which are the mixture of RLC elements. Mixture, that means that mixture includes resistors, inductors and capacitors. In time domain, we already seen that if you use only the resistors, connection of these serial connected resistors, you can replace just one resistor element, equivalent element. If only the inductors are connected in serial, so you can replace it with one inductor. Those we have seen in time domain. So let's go in details now. So we've got to move to open board here. Right time to open. Go to open mode. Open mode. Open mode. Okay. Here. Let me clear this previous one. So just remind you what is the serial connection is from time to time. Students, they mix those concepts. If two elements are connected in serial, means these two elements, let's A and B, two elements here. We say those two are connected in serial if one of the terminals of those two elements are connected together, like that. And there is no other element connected to that node. So that means there won't be any other connection like that. So I can show it like that. This is not allowed. Only those two are connected to that node. Then A and B elements are called serial connected. So this is an example for this. These n elements are connected in serial, and we already know that in any domain you are in, the element parameters written on the elements are impedances. So for the resistor, so this Z impedance here is this in the definition relation, isn't it? So the coefficient of the current of an element is impedance. That impedance could be either R or SL or 1 over SC, isn't it? It could be a capacitor, it could be an inductor, it could be a resistor. So you're going to write these impedances on them, not the admittances. You see that later on, if you write this definition relation in this form, then this is called now admittance Y. We do not write these admittances on the top of the element. We only write the impedances. So Y could be 1 over R or 1 over SL or SC. So how we are going to add this? I'll tell you the properties of serial connection here. Okay, written in English, but I can transfer it in English. Written in Turkish, I'll transfer it to Turkish. So the equivalent impedance is sum of the serially connected impedances. So that is it. How we are going to find that? We have done it for the time domain and frequency domain, so I'm not going to repeat it here. So in this, the number of nodes we've got, whatever the nodes we've got here, is going to be reduced to just one node. There are many nodes here, isn't it? When you replace these impedances with just one equivalent impedance, then all these nodes disappears, only one node replaced with all these nodes, apart from the ground. Ground is common here. So all these nodes disappeared and those two left here. So we could say that serially connected elements currents are the same. So if you take the element current direction, that direction, so it's going to be equal to that I. So you can consider that I as a loop current. So this loop current is the same as Z1 current, Z2 current, Zn current. Or you could prove it by using the Kirchhoff current law equation. So that's a conclusion saying that serially connected elements currents are the same. What is changing, what is not changing? So in here, this VAB voltage are common in this figure and this figure. So these voltages are going to be the same. So what I am saying is that if you connect a voltmeter here, and if you connect a voltmeter here, the voltage that you measure here and here are going to be the same. Similarly, these currents, this current here and this current here, if you put an ammeter here to measure that current and ammeter here to measure the current, those two currents are going to be the same. They're going to be the same. Why is that? This is the definition of equivalence, isn't it? If you remove all these impedances from the circuit and replace it with this equivalent impedance, this current and this voltage is not going to change. So let's come to parallel connection. Remind you what parallel connection is. Parallel connection, if two elements corresponding terminals are connected together. So that means this terminal and this terminal connected, and the other terminals are also connected. So you're going to have, so you can consider that one is just one node, isn't it? So two nodes here. So if it is Z1 and Z2, or A, B elements, Z1 and Z2 or A, B elements are connected in parallel, we say. So we are saying Now the conclusion we can get out of this, the admittances, I'm not going to prove it, but you can say that if n elements are connected in parallel, those n elements equivalent element admittance is equal to summation of all these parallel connected elements. So that is it. But we are not saying Z here, and up here we said we normally do not write Y1, Y2 here. So normally we are going to write 1, Z1, Z2, Zn here. And we are saying the equivalent of this is the admittance summation of the admittances. So another way of saying it, if you write it for the impedances case, so equivalent impedance Z equivalent is equal 1 Y1 Z1 1 over Z1 1 over Z2 1 over Zn. So 1 over Z, as you see here, gives you the admittance, so you can say that Y equivalent is Y1 plus Y2 plus Yn. This has already been proved in time domain and frequency domain. I'm not going to repeat it here. So when you compare those two, replacement of the admittance, parallel connected admittances with just one admittance, tells us that the n number of loops are reduced just one loop. So that means number of loops or meshes, many of them disappears except one, isn't it? So you can use that information in S-domain analysis for the circuit which have parallel connections in it. So the another thing that we can say for the parallel connections are all the elements voltages, parallel connected elements voltages are the same. So this element, this element, this element connected between those two terminals voltage is equal all these element voltages. What is not changing, this VAB voltage in this circuit and this circuit are going to be the same. Similarly, these two currents are going to be the same. That's the definition of equivalences then. So if you replace all those with one equivalent, those two is not going to change. In order to say that that is equivalent to this. That is, so okay, these are the serial parallel connections. How we are going to use it in practice, that's an example, practical example that we are going to examine. In this circuit, what you see, in this circuit, what you see, those two elements are connected in serial. If you replace it with the equivalent, then those two, if you first, this is time domain circuit. We are going to transfer it to S domain. In S domain, those two are connected in serial, replace one element, and then this element connected to 20 ohm resistor in parallel, replaced with the equivalent. And now this is connected to 10 ohm in serial, so you can replace those two with this one. So let's do it step by step. First of all, that is, what is the impedance of this in S domain? SL. SL is 100 millihenry, millihenry 10 to the power minus 3, then 0.1 S. That's the one. So let's come to capacitor. Capacitor impedance is 1 over Sg is equal 1 over Sg C. What is C? 100 microfarad. 100 micro 10 to the power minus 6. This becomes minus 4. move it to the numerator, sorry, it's going to be 10 to the power 4 over s. So that's this one. So 10 and 20 is not going to change, and that is time domain voltage, and that is S domain voltage. So this is time domain circuit dim, and this is S domain. In S domain, we are saying those two are connected in serial, so it's going to be summation of those two impedances, which is Z1 plus Z2, so 0.1s plus 10 to the power 4 over s. So you end up with this. So that is the same as this. Then those two are connected in parallel. So it's going to be Z1 multiplied Z2 plus Z1 Z2. So that's going to be 20 times this, isn't it? S squared 10 to the power 5 10s, and the summation of those two. If you do the calculation, so you're going to end up with this. So this impedance is going to be conclusion of this. You do it by hand, so that is you've got to do a bit calculation here. The resulting calculation is this. So these two are connected in serial, so it's going to be, so this one is 10 plus this, isn't it? 20 times s squared 10 to the power 5 over s squared 200s 10 to the power 5. So since Vs is known, Vs is this, so we can calculate this current. So this current is Vs over this, isn't it? So if you do this calculation, you're going to end up with this. So Is is this. So you can say that this Is is minus this I1s is minus Is. That means this element independent voltage source current is the negative sign of this calculation. If you do the Kirchhoff current law equation, if you write the Kirchhoff current law equation for this node, so those two currents are equal to each other except the sign. So okay, we calculated this current. So I found we already know that independent voltage source voltage, and we calculate the current. But our aim is the analysis of this circuit, not this. So that means, can we calculate all the other elements current and voltages? This is our problem. This is what we understood from the analysis of this given circuit. So how we are going to transfer that information to find out all the elements current and voltages is easy. We are saying if you calculate that current, so you can calculate 10 times that current gives you that voltage, isn't it? So you found this current, this element current and voltage. This voltage is known, independent voltage source, which is this, minus this voltage I just calculated. So it's equal to that voltage. That voltage is 20 ohm resistor voltage. If you divide that voltage to 20, you're going to get this current, isn't it? So we calculate current and voltage of this element, current and voltage of this element. So if you write the Kirchhoff current law equation for this node, you can calculate this current, isn't it? Because these two currents are known, so you can calculate this current. This current is the inductor current. So you found the inductor current. Multiplied with the inductor impedance, you get inductor voltage. So inductor current is equal to the capacitor current, since these are connected in serial. So if you know the capacitor current, so if you multiply it with the impedance of the capacitor, you get the capacitor voltage. So with those steps, we calculated all the elements current and voltages. That's why it is a useful tool for the serial connection, serial parallel connection, contribute us to do a analysis of a serial parallel connected circuit. Not good for all type of circuits. If there is a serial parallel connection in a circuit, then we can get that benefit. So you might say that, okay, it seems a bit good in S domain. What would happen if you do the analysis of this circuit in time domain? So there is one inductor and one capacitor here. It was going to be second order differential equation we were going to write for the analysis. That's going to be state equation, we call it. These state equations, if you solve it, you can find it capacitor voltage, inductor current. If you find the capacitor voltage, inductor current, then you can calculate all the elements current and voltages. So we were going to solve a differential equation. In here, there is no differential equation. That is the benefit of being in S domain. So that is the end of this frame video.